Happy Monday. Welcome back, everyone. So I believe we finished with 10.6 last time, and we were going to jump into 10.7. Okay, so 10.7. We're going to talk about vector functions and space curves. There we go. Okay. All right, so rather than how we did a line last time, so kind of recall that to do a line, you're in R3, 3 dimensions, and we had some straight line here. What we did was we had some arbitrary vector that pointed to an arbitrary point on the line. We had a vector that pointed in the direction of the line, snapshotting. There we go. And this allowed us to characterize this line by any arbitrary vector that kind of followed along, right? And we called that this vector R. Well, now let's do a kind of similar scenario, except this time we won't just talk about a line in R3, but rather a curve. So it could be kind of wonky. Maybe it starts over here. Doing the straight line tool again. It starts over here somewhere, and then maybe even kind of does like a loop, and then maybe comes out this way, and we're just kind of traversing this line or this curve. This. So you might even think of it as like a particle. A particle is moving along this curve, right? And any point here, I might be able to kind of characterize as a vector that's pointed to it. And we'll still call that R. But specifically, this point we'll call P, and it has some coordinate that might be defined parametrically as a function of t in each of its components. So we'll have an f of t, a g of t, and an h of t. And that all kind of details how this particle moves along this curve here. Well, the vector that's pointed to this point P, we can write as R. So the vector pointing to P at time t is R of t, f of t, g of t, and h of t. Now, I kind of want to talk about this time aspect. You don't have to think of t in terms of like the flow of time, right? T is just a dummy parameter. But a lot of times what we can do is assign that dummy parameter something physical, like the flow of time, right? So imagine a particle is moving along the curve, right? It's moving, so you kind of think of the flow of time. That doesn't necessarily need to be the case. It's just some dummy variable that we're using, some parametric variable. So this R of t function, this is a vector valued function. or just a vector function. So notice that I input a scalar into this and I get a vector back. This has component functions another definition. F of t, g of t, and h of t. Right, so these are scalar functions, the type of functions that we've seen in Calc 1 and 2 and everything that happened before that, right? So these, you put in a scalar, you get a scalar out of them. So the curve is then traced by this r vector as a function of our parameter t. Right, so imagine we're looking back here, and I'll scroll down in a second again. So imagine we're at some point, and as I increment t, I kind of just start to trace out this curve because my vector will always be pointing to the particle as it kind of travels there. Okay, so we're going to do our first calculus thing in R3. We're going to talk about limits. I guess saying that it's in R3 is kind of maybe a little bit of a stretch. We're going to talk about limits that act on this parametric parameter t. So since our vector function r of t is of only one variable, right? All it relies on is just t. The limit so we can have the limit as t goes to some value a of r of t is equal to the limit as t goes to a of f of t, the limit as t goes to a of g of t, and the limit as t goes to a of h of t. So if we take the limit of this vector function, basically we're taking the limit of each of its components. Now this is so long as, or provided the limits of the components exist. That's the only time we can say that this limit is equal to this over here, right? The limits have to exist for it to make sense. So Let's look at an example. If we have that this vector function, r of t, is equal to cosine of t times I hat plus sine of t times j hat plus t times k hat, find the limit as t goes to pi over 4 r of t. Okay. So the limit as t goes to pi over 4 of my r of t, I can write this as the limit as t goes to pi over 4 of cosine of t times I hat plus the limit as t goes to pi over 4 of sine of t j hat plus the limit as t goes to pi over 4 of t k hat. So luckily, all of these components are continuous functions, so it's pretty easy to take the limit of these guys here. Here I have root 2 over 2 I hat plus root 2 over 2 of j hat, and then pi over 4 k hat. So that's our limit. So another question that I kind of want to ask involving this example is, what does this vector function look like? What does this r of t kind of trace out? So take a look and kind of maybe even start to think about what this possibly could look like. I've got, in the x component, I have this cosine, right? It's this periodic function, right? As well as sine of t in this y direction. And then I have this linearly increasing function t in the z direction. So if you did any kind of like parametric stuff in Calc 2, if you had just in the xy plane cosine and sine, you might be thinking to yourself, oh, this traces out a unit circle, right? A circle of radius 1. But now I've got the z component, and this is steadily increasing here. So you could kind of imagine that this draws this circle, but at the same time, it's slowly moving upward. So it starts to look, let's kind of do a sketch here. There's some questions, and I can answer them as soon as I'm done sketching this guy. All right, so I'm going to try my best at trying to draw this thing. So it's like we're drawing this unit circle, but we're steadily increasing our z component, kind of like going in this direction here. This is known as a helix. Okay, so here are some of our questions. Are there examples we will see where the limits will not exist? What do we write in those cases? If we have that any of the component function limits do not exist, it's that the limit doesn't exist for the R of t function. So that's why we can't really say it's equal to it, right? We're just saying that the limit does not exist. Should we be reviewing Calc 1 on how to find the limits, the limit basics for harder limit problems that may occur? If you're kind of foggy on your limit taking strategies, yeah, I would review those. We are going to talk about these limits for parametric equations, but down the road, we will talk about limits in R3. Like if I approach, what's the limit when as I am approaching this point in R3 rather than just like say x is equal to 1, maybe I'm looking at, x is equal to 1 and y is equal to 2, right? So it's a little bit harder in that case. We'll kind of see it when we get there, but we'll definitely need those limit taking strategies from Calc 1. Yeah, this whole class is just a generalization of Calc 1 and 2. Okay. So let's talk about continuity. So a vector function R of t is continuous at a point where t is equal to some t naught if the limit as t goes to t naught of r of t is equal to r at t naught. The function R of t is continuous if it is continuous at every point. In its domain. So you've kind of seen this before in Calc 1 for continuity. So this is just kind of bringing us up to speed for these vector functions as well. If we have that the limit is equal to the actual function at that specific point, we say that the function is continuous at that point. If that's true for all points in its domain, then it's continuous. So in other words, if I have that r is equal to my f of t, g of t, and h of t, then r of t is continuous if and only if, which we'll kind of write by this backward and forward arrow, the component functions are continuous. So if you can write f, g, and h as these continuous functions, then we know that the vector function should be continuous as well, right? And that just stems from the fact that if we have that these functions are continuous, they certainly are continuous at every single point, which means our R function is a continuous vector function. So this is kind of the layman's terms. Kind of bringing us up to speed from our Calc 1 continuous definition. Okay. And now with that, let's talk about some derivatives. So let's consider our vector function r of t with component functions f of t, g of t, and h of t. And it points to a traveling particle. Right, so think about our plot from up at the beginning of the lecture. We're tracing out this curve that's defined by this r of t, and you can kind of think of where it's pointing at time t, this location of this particle. The difference in position from time t to, we'll kind of put this time t to time t plus some change in time delta t is we'll call this the change in r, delta r, is r at t plus delta t minus r at t. Right, so that's the change. This is the difference in position here. Well, we can write this in its kind of component form. So this is f of t plus delta t, g of t plus delta t, and h of t plus delta t minus f of t, g of t, and h of t. Keep writing. Write this as the single vector f of t plus delta t minus f of t, our g of t plus delta t minus g of t, and our h of t plus delta t minus our h of t. Okay, so let's keep this in mind while we're moving forward. So that's the difference in position, just given a small change of time, delta t. the derivative of r of t with respect to t is the velocity. Right? We can kind of think of that from physics 1 and just even calc 1, right? We had some f of t function or you know, some thing that described the position as a function of t. We take the derivative with respect to time, we end up with this velocity. Well, we can write this as dr dt, or another way of writing this is r prime of t. And by definition, this is the limit as delta t goes to 0 of the change of position here with a small amount of change, delta t, so t plus delta t minus r of t over delta t. Well, we just here defined what that difference was, so let's go ahead and write that in. So this is the limit as delta t goes to 0. I'll write it in terms of its components. F of t plus delta t minus f of t. And what I'll do is I'll bring in this delta t to each one of these components, multiplying by this 1 over delta t. So we have g of t plus delta t minus, in that parentheses, minus the g of t over delta t, and then h of t plus delta t minus h of t divided by delta t. Okay. So what we know about limits is we can apply this limit to each one of these components. Now, if you do so, this should kind of remind you, oh, this looks like the definition of the derivative just from Calc 1, right? So it turns out, you could probably expect this all along, that this is f prime of t, g prime of t, and h prime of t. Once again, we'll just have this caveat, provided that f, g, and h are differentiable. So if we needed to take the velocity of, we're trying to find the velocity of this particle that's moving along this curve that's given by this position vector r of t, then the derivative of each of these components comprise the velocity vector, right? And that will give us the vector where the velocity is pointing. So velocity is a vector, right? It has a magnitude, the speed that the particle has, and the direction that it's traveling in. Okay, so we have a question here. When solving, do you want us to use the limit definition, or can we skip straight to the usual way? Usual way is fine, yeah. This is just so we can derive the fact that, oh, hey, it made sense that, you know, we were looking at this vector function, and if we took a derivative we actually got the derivative of the components. But right, and in practice, go ahead and do it the good old non-limit way. You can just differentiate. Okay. So, like I said, this vector that illustrates this velocity points in the direction that the particle is traveling in. And that's important, right? We're going to do a lot of things with that, right? So sometimes when we have a vector it's that important, we like to make it have something that kind of characterize the unit vector in that direction. So we'll define one of our first big unit vectors here. The unit tangent vector is then, we write as a capital T. It is R of t prime over the magnitude of R prime of t. Right, so remember, that's one trick that we learned about making a unit vector is we take some vector and we divide it by its magnitude, and boom, we have a unit vector that's still pointed in the same direction. Right, so we have our velocity here, and since the velocity is pointed in the direction of travel, our unit vector is simply a unit tangent vector. It is pointed directly tangent to the curve in the direction that the particle is moving in. And that is fairly handy when we're doing problems involving kind of motion. Okay. Let's go to a new page because we're going to talk about differentiation rules. Okay, so differentiation rules. So let's talk about what happens when we take derivatives of these vector functions. So given that u and v are differentiable vector functions, we have some constant c, so some scalar c. So this is c exists in the reals. And f of t is a differentiable function. So it's a differentiable scalar function. So here are some of our rules. One, if we take the derivative with respect to time of c times u vector, you can write this as c times u differentiated with respect to t. Right, so just kind of how you think differentiation works with functions and scalars. Right? 2, if we take the derivative of f times u. So this time we have a scalar function and a vector function. It's just like the product rule. We get df dt times u plus f times du dt. It's nothing too crazy there. 3, we take the derivative of u plus v, we get du dt plus dv dt. Okay, so those seem to line up with our logic from how differentiation works with scalar functions, right? So nothing too crazy going on here. Well, we talked about new operators specifically for vectors, the cross product and the dot product. So we're going to look at 3 different scenarios here. We're going to do kind of proofs through each one of them. What about the derivative of u dotted with v the derivative of u crossed with v and the derivative of u with a scalar function f inside. So let's go one by one and see what we can come up with for the laws of how this differentiation works. So let's start with the dot product. So what I'm going to do is just kind of do the dot product out here. So I have d dt of, and imagine we're in R3, but this kind of generalizes to just Rn, any arbitrary dimension. We can have u1, v1, plus u2, v2, plus u3, v3. And these could all still be scalar functions in terms of time. So we're going to have to do a lot of product rules here, but I'm going to write it in such a way. So we have u1 prime v1 plus u2 prime v2 plus u3 prime v3 plus u1 v1 prime plus u2 v2 prime plus u3 v3 prime. And I've kind of wrote it this way because we can look at each of these groupings here. So this thing right here, this is u prime dotted with v. And this thing here, this is u dotted with v prime. So at the end of the day, we can just write this as u prime dotted with v plus u dotted with v prime. So it looks like the dot product kind of works kind of like a product rule, right? So now I just have these dot products in here. Okay. So that was, I guess you can call this rule 4 from above. Now let's look at the cross product. The cross product is going to be a little bit harder than this. We're actually at 1:25. So before we get into this, why don't we take our 5-minute break now, and then we can come back and do the cross product rule. So go ahead, use the restroom, get yourself some water, and we'll be back in about roughly 5 minutes. Okay, so let's jump into this cross product rule. For this, we're actually going to use the limit definition. So we have d dt of u crossed with v. I'm going to write this as the limit as delta t goes to 0, u of t plus delta t crossed with v of t plus delta t minus u of t crossed with v of t. This is all over our delta t. Okay, so I'm going to, in the numerator, I'm going to add and subtract the same quantity. So basically just doing nothing to the numerator. Let's kind of scribble that down. I'm going to add and subtract u of t crossed with v of t plus delta t in the numerator. So being really sneaky here. This is now the limit as t goes to 0. I'm actually going to write the delta t out, or the, 1 over delta t on the outside here. So now I have u of t plus delta t crossed with v at t plus delta t minus u of t crossed with v at t plus delta t plus u of t crossed with v of t plus delta t. And then we have this minus u of t crossed with v of t. So now I'm going to group up some terms in particular. So this is the limit as delta t goes to 0. So notice that if I look at the terms that are right here, these two terms, on the right-hand side, I have the same thing of my cross product, right? I have this v of t plus delta t on both of these two terms. So in fact, what I can do is write it as u of t plus delta t minus u of t over delta t, and I'm crossing it with t plus delta t. So those are the first two terms, and I use cross product rules to kind of group these in together. Now this next term, notice that they both share a u of t on the left. So I can write this as plus u of t crossed with v of t plus delta t minus v of t all over delta t. So I grouped it from the left element here. Okay. So if we're talking about applying this limit here, this term here looks a lot like u prime, right? And as delta t goes to 0, this thing just becomes v of t, right? This delta t will go away. Over here, we'll just have u of t, but this right term here looks like v prime. So in fact, we get that this is du dt crossed with v plus u crossed with dv dt. So it looks like the cross product also goes by a similar product rule, but we had to take a little bit longer of a journey to kind of illustrate that. So this is our, I guess, our rule 5 here. And then finally, we were asking about kind of this equivalent chain rule for vector functions. So if I have the derivative with respect to t of this vector function, but it has a scalar function f of t inside of it, well, let's write that in terms of its components. This is d dt of the vector u1 with f of t in it. This is u2 with f of t in it. And this is u3 with f of t in it. And we're assuming that we're in R3, but this generalizes to Rn. So if I want to take the derivative of this vector, we can take the derivative of each of its components. So in its component form, we have just the normal chain rule, so f prime of t times u1 prime of f of t, f prime of t, u2 prime with f of t, and then f prime of t, u3 prime f of t. The question, so rule 5 is the same format as rule 4, but with cross products instead of dot products. Yep, with the same thing. They because it's really nice that they are like the dot product and the cross product. They basically are just the product rule, but for vectors here. All right, so back to the chain rule. So we just use the chain rule, the scalar version of the chain rule for each of our components here. Now they all share an f prime in common. So I can write that as f prime of t multiplied by u prime with f of t in it. Right? And that kind of looks exactly like a chain rule, right? If u was a scalar function, we wouldn't have this vector here. But it works very similar, right? We still have the derivative of the original thing with f of t in it times the derivative of what's inside, right? This f prime. Okay, and that could be our rule 6. Okay, so that's for rules for differentiation. Let's go to a new page here where we will discuss vector functions of constant length. Okay, I can go back to the last page here for a second, just so you can scribble down. Okay. So vector functions of constant length. So let's start by, we're going to imagine, right in that E show, there we go. Imagine the particle is now bound to the surface of a sphere. This means that the magnitude of our position vector for our center of the sphere is at the origin is some constant. Right? And it doesn't necessarily need to be a sphere, but it's a good kind of visualization. I have some position vector that is always a constant. Well, its magnitude is a constant, right? But it could be pointing to whatever as long as the magnitude remains the same. So here, we're going to use this aspect a lot later. So we can also note that if I wanted to take the derivative of the quantity of r dotted with itself, there's two ways I can kind of think about this. One is that this is the derivative of the magnitude of r squared. That's the definition of dotting something with itself, because we have the magnitude squared. Well, this is the derivative of a constant because the magnitude is a constant, so we just get 0. Right? Another way to do this is to do what we talked about for the product rule. This is dr dt dotted with r plus r dotted with dr dt. Or because the order of our dot product doesn't matter, we can just write this as 2r. Just going to write that r a little bit better. 2r dotted with dr dt. Okay, so we did it two different ways, so the end results need to be the same. So I know that r dotted with dr dt is equal to 0. Okay, so if we remember back to our dot product properties, if I have that the dot product is equal to 0, that meant that the two vectors were orthogonal. So this means that r and dr dt are orthogonal. So this is only true for vector functions with constant length. So this isn't always true. This is over the special circumstance if we have that our r of magnitude is equal to some constant value. And it kind of makes sense if you think about it. If you are this particle that's kind of restrained to the surface of the sphere, kind of like if the Earth was, really, really smooth, right? The r vector points from the center of the Earth out to us, but we can only move along the surface here, which is exactly tangential to the surface that we're moving on. And that's always going to be orthogonal to that r vector. It's always going to be at this 90-degree angle between the position vector and my velocity vector, where I'm kind of pointed and where I'm kind of traveling in, which is pretty cool. And we're going to use this aspect later for some proofs as well. Okay, so that brings us to some integrals. We've talked about derivatives. Let's look at some integrals. We can express integrals component-wise as well. So imagine I have some integral of a vector function r of t dt. Well, I can write this as some capital R of t plus c, where I have my components, the integral of f of t dt, the integral of g of t dt, and the integral of h of t dt, where we say that this r, this capital R vector function, is the antiderivative of little r of t. So just like derivatives, our integrals here are kind of like this component-wise operation. So let's do an example. We have the integral of the vector cosine of t, 1, negative 2t dt. Well, this is the integral of cosine of t dt, and then I have the integral of 1 dt, and then I have the integral of negative 2t dt. So I can do each of these integrals separately. So we have sine of t plus c1. We have t plus c2. And then we have negative t squared plus c3. Oh, and let me double check that yeah, okay. So these aren't necessarily all the same constant. So that's why we have to be a little bit careful here by labeling them C1, C2, and C3. And then in other words, we can just say that this is sine of t, and negative t squared plus some vector c, right? Where its components are C1, C2, and C3. Okay, so can I scroll up to above the example? Right there. So these are indefinite integrals, but we can also talk about definite integrals, and they work very similar. So definite integrals. So imagine that I've got some integral from a to b of this vector function r of t dt. This is also component-wise. So we have each of our components, dt, there we go. And here's an integral from a to b of h of t dt. Okay, or we can kind of write this in terms of its antiderivatives again, where we have this capital R of t evaluated at t equals a and t equals b, or capital R of b minus capital R of a. Okay, another question. What does the integral represent? Like how the derivative represents the velocity of the particle moving in time. We'll actually talk about how this kind of works in the next section as well. But imagine if you had a velocity, right? And you wanted to, from that, find a position vector, just like how we've done kind of like Calc 1 or maybe even Physics 1. Right, very similar concept, right? It's kind of just this generalization to a higher dimensionality, but do not think about it in terms of area underneath a curve, because t is this parameter, right? It doesn't necessarily exist in these x, y, z space. We'll talk about what happens when we do integrals in the Cartesian coordinate system in chapter 12. So we have to go through a whole chapter before we get there. But just think of it as your kind of generalization of, oh, if I've got this velocity vector and I integrate it, this kind of tells me the distance that I might have traveled, right? But now it's a kind of generalization of this thing. Okay, so let's do a quick example where we do some definite integrals. So if I look at the integral from 0 to pi of cosine of t, 1, and negative 2t. So it's no coincidence that this is the same integrand. So we already know the antiderivative. So we know that this is equal to the vector sine of t, and negative t squared, evaluated when t is 0 and pi, where we get sine of pi minus sine of 0, pi minus 0, and negative pi squared plus 0 squared, or the vector zero pi negative pi squared. Okay, and that's it for section 10.7. So we have about 20 minutes left, so we'll actually get started with section 10.8. So let's jump to a new page. So I'll give you guys a second just to finish writing up here. Okay. So we have section 10.8. We're going to talk about arc length and curvature. So kind of recall from Calc 2. So in Calc 2, we found the arc length of parametric equations in R2. And we found it that this length, this arc length here, was from some a to b, the integral. We had the square root of f prime of t squared plus g prime of t squared dt. Right, so if you had some kind of parametric curve in R2, this was the kind of formulation for finding the arc length of this curve from the time A to time B. So it's probably no surprise that the kind of generalization of this thing here to R3 is just going to tack on an additional term. In R3, we arrive at L is the integral from A to B, the square root of f prime of t squared plus g prime of t squared plus h prime of t squared. dt. But now we're a little bit smarter than we were in Calc 2. We've got vectors now at our disposal. And I want you to stare at that integrand because it looks like the magnitude of some kind of vector, right? And in fact, it's the magnitude of r prime. So actually in Rn, some arbitrary number of dimensions, this is how we write the arc length, right? If we have parametric equation that's given by r of t, then the arc length is simply the integral over the magnitude of r prime of t. Pretty neat. So let's do an example. We're going to find the length of one turn of the helix. R of t is equal to cosine of t sine of t and t. So the helix has made a return, and we're going to try to find the length of one rotation, one turn of this helix. Okay, so the first thing we need is this r prime. So first, we find r prime of t. This is negative sine of t, cosine of t, and 1. Okay. So now I want to find the magnitude of this vector. And it might be a function of t. It's a square root of negative sine of t squared plus cosine squared of t plus 1. Well, this negative sine squared is just simply a sine squared. The negative goes away, right? And then I have a sine squared plus a cosine squared. Right? So I have sine squared plus cosine squared. That's equal to 1. So this just looks like I have the square root of 2. And we're going to see a lot of sine squared plus cosine squared. So it's a good thing that we can remember that that quantity is always going to be equal to 1 here. So this could have been a function of t, but it turns out for the helix, it's really nice the magnitude of r prime is just simply this constant, root 2. So all that remains is to integrate. But I need to integrate from a to b. This is a definite integral, right? So if I want one turn of the helix, I should just get I should choose a and b such that I sketch out one turn. I think probably the best would probably be 0 to 2 pi, although you could do any variant as long as you do 2 pi radians. So we can go L is equal to the integral from 0 to 2 pi. We have the square root of 2, which is the magnitude of r prime, dt. Integrating this is amazingly easy. We just have the square root of 2 times t from 0 to 2 pi. So then we just get 2 square root of 2 pi. And that's the length of one revolution of this helix. Pretty cool. Okay. So give you guys a second to write that, and then we're going to start talking about curvature. Go up just a little bit. Okay. Curvature. We call some vector function r of t smooth if the derivative r prime of t is continuous and it's never equal to 0. Recall our unit tangent vector So remember this from the last section. This was our r, oh, it should be r prime, there we go, r prime over the magnitude of r prime. Remember, that's the vector that just points in the direction that the particle is traveling in, right? It's tangential to the curve r of t. The curvature r of t is a measure of how quickly the curve changes direction. With respect to space. So imagine you've got, you can even talk about the helix, right? The helix certainly has a curvature to it, right? It's wrapping around, it's spiraling upward, right? But we have to be a little bit careful when we're talking about the rate of change or like how quickly something is changing, right? Because this parameterization that we've introduced talks about how quickly something changes with respect to time, right? The velocity is how quickly the particle is moving with respect to time, not how quickly the path changes with respect to space. Like how sharp of a turn, if you're in your car, are you making, right? It's not how quickly you're making the turn, but how quick does this turn make? Okay, so to do this, we define it as the magnitude of the rate of change of the unit tangent vector with respect to arc length. Because arc length doesn't care how you parameterize the curve. The arc length is a constant that is native to the curve itself. So it's something that we can definitely use to kind of define how we change with respect to in space, right? So arc length is inherently a part of the curve, whereas our parameterization is just this dummy variable, right? We can't really utilize that all too much. But the unit tangent at that point will always remain the same, regardless of what we've parameterized with. As long as it is referring to the same point in space, it will always be the same. And curvature is defined as a scalar, and this is a kappa. So it is the magnitude of how the unit tangent, capital T, is changing with respect to arc length. Arc length is typically denoted by ds. So an infinitesimal amount of arc length is referred to as this ds in this context. Okay, so this is one definition that we'll see of curvature in this section. This is certainly not the best way to calculate curvature, but this is by definition the most simplistic form for curvature. So let's see if we can rewrite this in terms of things that we know how to calculate right off the bat. Okay, so we've got about 7 minutes left, so I think we've got a little bit of time to do some derivation here. However, we can write dt, this is a little confusing, how the unit tangent changes with the parameter t. So taken with respect to the parameter t, but this is the unit tangent, capital T. This is d capital T ds ds dt. So that means that I can write dt capital T ds as the fraction d capital T dt over ds d lowercase t. So the magnitude, our curvature, is the magnitude of how the unit tangent changes with respect to time over the magnitude of how arc length changes with respect to time. And with that, that's another way to kind of define curvature, but we're not quite done yet because I don't like how we've expressed this so far. We're going to keep going. We're going to keep kind of fiddling with this until we get some really nice results. But we're going to end the lecture there, and then we're going to pick up tomorrow and probably finish up this section. So then all that remains is 10.9. Okay. So let's stop the recording there.